Hi everyone. This is just a tutorial for you for chapter 10 to keep us on track and give you some tips and understanding and explanation of what's going on with hypothesis testing. So a really quick review of chapter 9, and you have a tutorial on Cougar courses for you about that and helping out with the homework there, is to remember that chapter 9 is all about single samples. So we just had one sample, but there's something about that sample. We have a hypothesis that we're going to compare our sample to. And that hypothesis is usually is usually a population mean of some sort that we have, but we don't have the population standard deviation. And so that error within the denominator, we have to estimate using the standard error of the mean. So what we do is we're comparing, and this X bar here, the X bar in this formula is also notated sometimes as a big M, and that is your sample mean, your single sample that you took. And you're comparing that from your mu, your hypothesis. You're stating this in your null hypothesis. And you're dividing that difference, that mean difference, over any error. And what that's going to do is it's going to give you a calculated t. And then essentially you compare that t to the critical value and you determine if it was significant. And so here's a refresher on those variables. So we build on that idea in chapter 10. Only we build on this idea in two different ways. The first way is with an independent t-test. So an independent t-test is no longer a single t like we had above, right? This is a single t. We just have one x, one mean, or one m, right? X bar m. In an independent t-test, we are now comparing two independent groups, group 1 and group 2. So we have an average for group 1 and we have an average for group 2, and we want to see if these two groups significantly differ than what is beyond chance. Right? Everything in statistics is about probability. So basically we compare these mean differences, can also be notated with a big M, but is usually notated with an X bar. And we compare that to the mean set in our null hypothesis. So those are those population means. Usually it's set to 0 if it's non-directional, or it might be greater than or equal to this. So the error in this case is the standard error of the mean differences. So what you're getting at to find the standard error of the differences is you're still comparing, just like in a single t, the variance, only because we now have two different groups, we have to pool their variance. So you're going to take the pooled variance over its respective sample size for sample 1 and sample 2 and take the square root of that. Well, how do you find a pooled variance? Well, you have to add the sums of squares and take that with respect to the degrees of freedom. Degrees of freedom on an independent t-test are different than normal. So you have to take each group into consideration. So for the amount of people in the first group, as well as the amount of people in the second group, that gives you your degrees of freedom. Your sums of squares is calculated by taking all of the x's squared. So you'll do this for each group, right? So you'll have a sums of squares in independent groups. You'll have a sums of squares for group 1, and you'll do another one for group 2. So you'll do this 2 times. So you'll take all the scores from group 1, right? That sum of x, and you'll subtract the quantity of x, the whole thing squared, over n. Remember all those columns that we did? All the things you were tested on in previous exams? This is what we're building on. So then you kind of work backwards through the formula, and it gives you your calculated t, and you compare. So what's the other t? The other t is a dependent t-test. A dependent t-test says that this is the same group of people, essentially. So we have a score for them on time 1, something happened, we want to measure time 2. Is there a difference? In a perfect world, we get to measure the same people time 1 and time 2, and that's called the dependent or repeated measures t-test. But sometimes in the perfect world, we can't get people twice, so we match people. So you can also have, this also works with match differences, match pairs. But for our example today, we're going to talk about the same person twice. So essentially, it's the same setup. What is our mean, our sample mean, compared to what we're hypothesizing, and is it that difference large enough to be by chance? Only because these are the same people, we're only comparing the difference, the average difference for all the people in our score, and that's your mean difference here compared to the mu, or the population difference. And instead of a standard error of the mean, or standard error of mean 1 and mean 2, we now have standard error of the mean differences. And so same thing, you have all these formulas. How do I find that? Well, you need your variance divided by the sample size. Well, how do I find my variance? Well, same as before, you take your sums of squares divided by degrees of freedom. Only now we're back to degrees of freedom n minus 1, because we're just interested in these different scores for these number of people. They don't count twice. It's the same amount of people each time. So to find the sums of squares, instead of x's, you're actually summing the differences. And so when you're looking at repeated measures, or you're looking at dependent means, think about, it's all about the difference. It's all about the d within the formula. So once you calculate your t, right, you compare that to your critical t. And you'll need your alpha. You'll need to know if you want a one-tail or a two-tail. And you'll need your degrees of freedom, your respective degrees of freedom. And so what you do is you compare your calculated t to the critical t that was outlined by that information. And if it falls within that rejection region, you can reject the null, right? You found a significant difference between these groups. Another way to know how significant the actual level of significance is to calculate the p-value. And we have that p-value calculator provided on Cougar courses for you. And so you would enter this information, the means and the alpha you want and the tails, etc., and it will calculate that specific p-value for you. Well, so you found significance. Whoop-de-doo, right? By now you should know through the central limit theorem, law of large numbers, the higher your sample, the more likely you increase your significance. So if we just have people out there doing these massive samples, they're always going to get significance. Is it really significant? Is it really a big deal? How do we account for understanding how significant is this? Because it either is significant or it isn't, period. But what's the magnitude of this significance? What's the practicality of it? That's where you get into an effect size measure. So we're going to learn 2 different ways to calculate effect sizes for our parametric tests. And one of them is Cohen's D. Cohen's D is essentially asking about the practicality of this significance. Is it a small significance, a medium significance, or is this a large significance? Meaning that regardless of sample size, you're going to find significance. This is a pretty big difference. So essentially you're comparing your mean differences to the standard deviations, on average, how far those means differ. And by doing that, you get a number. And if it's 0.2 or less, it's a small difference, a small level of significance. 5, up to 5 is medium, and 8 or more, you've got large. Another way to do it, and this one's really great for t-tests, is to account for what percentage of variance is explained by the variable of interest, by the treatment, what happened. And so you take your t and you square it. You square it again in the denominator plus the degrees of freedom. If that number is less than 0.01, you've got a small, it's a small percentage. So, that percent is pretty small. It is significant, but if you have a smaller sample size, you may not find significant. So interpret with caution. Once you get into the large, a 0.25 or more, then what's happening is this variable is explaining more than 25% of the difference between your groups. And once you get up to that number, that's a pretty significant proportion of difference to be explained by one variable. And you can say with pretty much certainty that even with a small sample size, there's something to be said about this difference. So now that we know kind of the idea behind our t-tests and what's happening with our t-test, and we're going to do an example of an independent t-test. So remember, an independent t-test, you have two separate groups, right? We're going to compare group 1 and group 2. So our example today is on college students. And the data kind of indicates that sometimes you guys aren't honest. That would never be any of my students. I know that. So to test this, there's an experiment. And what they do is they have college students self-report the number of puzzles that they completed based off of the lighting in the room. And the idea is, in a dim lit room, you're gonna have an inflated number of puzzles reported because you know, the people aren't paying attention to you as much. It's a dim lit room, so you're more likely to cheat. So the idea is, depending on these groups of students, will we get differences between self-report puzzle pieces from the well-lit room versus the dim lit room? So in the dim lit room, I forgot to write, this is an 8. Yeah. And this one was actually a 12. Sorry. There we go. That'll help better. Erase you. Okay. So what we have is, you can see we have scores for each person in each group. So this person said 11. Oh, goodness. This person said an 11. This person said a 9, a 4, a 5, a 6, a 7, a 12, and a 10. So we have 8 scores in the well-lit room. We have 8 scores in the dim-lit room. The average, X bar M, for the well-lit room is an 8, and the sums of squares is a 60. The average for the dim-lit room was a 12, and the sums of squares was a 66. So now that the question becomes, is this spread, is this difference between this 8 and 12, given these 16 people that we have and the error inherent within, is this difference enough to say it's not by chance the dim-lit room, right, they're higher, they over-reported and inflated their puzzle completion, and they might be liars. So the first thing we have to do is we have to decide, are we going to have a non-directional or a directional hypothesis? Well, let's just go with non-directional, right? And let's call it an 05. We'll just keep it very conservative at this point. And this, you know, we'll just, the usual, you know, non-directional 05. So the first thing we have to do is set our null hypothesis. And our null hypothesis states that there is no difference, right? There's no difference. And our alternative says that there is a difference. We also have to know our degrees of freedom. So remember, in an independent t-test, because you have 2 independent groups, you have a more complicated degrees of freedom. n-1 plus n2 minus 1. So our degrees of freedom here, we had 8 groups in each, right? So 7 minus 1 plus 7 minus 1, or sorry, 8 minus 1 plus 8 minus 1 is 7 plus 7, or 14. It's our degrees of freedom. So now we know that we have to actually calculate and find our t critical. So we have to take our mean 1 minus mean 2, and we calculated that as 8 and 12. And we need to calculate the standard error of the mean. Well, how on earth do you do that? Here you go. You have to calculate, you kind of have to go backwards, right? So your standard error of the mean differences includes your pooled standard deviation over your sample. And you take that square root. Well, how do I get my pooled standard deviation? Well, your pooled variance is the sums of squares, 1, so the sums of squares for your first group divided by the degrees of freedom for that group, plus the sums of squares for your second group divided by the sums of squares, or the degrees of freedom for that group. So that was provided for us. Yay. So what we do is we plug in the 60 divided by our degrees of freedom, which is 7, and 66 for the second group divided by 7. So that gives us a pooled variance of 9. So when I plug in my pooled variance divided by the actual sample size now, the n, so 9 divided by 8 plus 9 divided by 8, I get a standard error of mean from mean 1 to mean 2 of 1.5. So now I know my mean 1 was an 8, my mean 2 was a 12. And my standard error of the difference between mean 1 and mean 2 is a 1.5. And I can calculate my critical, my t calculated, which becomes a negative 2.67. So now I have 2 different ways, as we said, to compare and find the significance level of this. So the first way is to actually look up that table within our book. And when you go to that table and you go to the T critical, as we learned in last chapter, you'll see that critical rejection region is a plus or minus 2.145. Remember, we did non-directional. Well, we calculated a negative 2.67, which falls beyond this negative tail. We said it was non-directional. It didn't matter which end. Significant. We get to reject the null. There is significant difference between these groups. They did report that DIM group reported significantly higher number of puzzle pieces completed, which lends us to say, y'all might be lying in that group. Are you liars? Let's find out. Well, how practical is this significance? What percentage does lighting explain, right? Because that was our variable. Well, if we take our T and look at it from R squared, we can say that we found a 0.33, right? So based off this T calculated, that is an incredibly large effect size, and lighting explains a third of the difference between these two groups. So it's pretty confident that we can say that students might be liars, at least in this group. Well, let's get curious. What if it was directional? I mean, we were saying that if it is a dimmer group, they are going to increase their number of puzzles. They're going to lie, so they're going to say more. So what happens if we make it directional? Does that change the significance or not? How do we play with that data and understand it? So we would put that our mean of dim, we would say, right, for the null, that it would be either less than or equal to the well. There's really going to be no difference between them, or the well lit might even be higher, right? But our alternative says no. The dim lighting is going to be higher than the well lit. We think that's really going to happen. It's not just going to be no difference. And this time we're shoving it into one tail, and we're actually going to be even more conservative with our estimate by dropping that alpha to a 0.01, because we're going to move that rejection range, right? So a 0.05, right, alpha would be over here. So we're getting more conservative. We're making it even harder to reject that, to find a difference and say, wow, this really is a significant difference. So then what we have to do is our T critical changes, right? We've put it in one tail, and our alpha is now a 1. So the T critical becomes a negative 2.62. So that pushed it back from that 0.5 in the two tails, right? And that dropped it. Well, our T calculated, we already did, is a 2.67. It still falls within that. And it makes sense. We found a huge effect size. So even pushing that significant level to an 0.1 and putting it into a one-tail test, we still found significance. So that's one example of an independent t-test, looking at differences between two independent groups. What happens with repeated measures? Repeated measures says we want to examine the same group twice. Maybe we get your score, we give you a treatment, and then we get your score again to see if there's a difference. Ideally, maybe what we'll do is we'll ask, you guys and compare, what's happening. You're going from a live statistics class to essentially a virtual class. Is this point in time going to be significantly different, hopefully for increasing your performance somehow? I don't know, but that's my hope. So in this way, in this example, what they examined was they want to know the effect of drugs with a drowsy label on reaction time for participants who have taken those drugs. Well, at first, they need to know their general reaction time without having that drug in their system. So X1, time 1, is the reaction time before the meds, and time 2 is the reaction time after the meds. And we only have 4 people in our sample. We have person A, B, C, and D. So at time 1, here's their scores. At time 2, here's their scores. Now remember, everything in the formulas for your repeated measures or your dependent measures t-test is all about the D, the different score. So we need to calculate that different score. These X's don't matter anymore. What matters is the difference between that one person from time 1 to time 2. So the difference for person A, they dropped, right? Their reaction time is got lower. They actually got better with the drugs, but everyone else clearly went up. Their reaction time increased. It took them longer, so they went up. So the question is these four differences, are they enough to say there was a significant difference from time 1 to time 2 after taking these drugs? So there's a couple things that you have to calculate. And this example is great because it's going to show you all the things, how to calculate a sum of squares and everything that we kind of brushed over on the last one, okay? So the first thing you have to do is set up your hypothesis. So we're going to make this a non-directional hypothesis, and we're going to do an alpha of 0.5. And so we're going to say our mean difference is 0. From time 1 to time 2, the drugs didn't have an effect. There was really not a significant change. Or we're going to say it's not, it did change. It's significant. It changed. And another important thing you always have to know is your degrees of freedom. Back to the repeated measures, it's back to just n minus 1. These are the same people twice, so you just have these 4 people that are varying. We just have persons A, B, C, and D. These aren't 2 independent groups. They're the same people twice. So it's 4 minus 1, or degrees of freedom of 3. So we need to know the mean difference because we know this is 0. So how do we calculate it? Your mean difference is the sum of all the differences divided by n, exactly like you'd calculate any mean, so that shouldn't be very complicated. So you go back up, you find your difference scores. You sum those to get a 64. You divide that 64 by 4, our n, and you get 16. So our mean difference is a 16. On average, people increased their reaction time by 16 points. So now we have 16 minus 0, but now we need to know how to get to the standard of the mean differences, standard error of the mean differences. And so that formula is the variance divided by n. Well, how do I get my variance? Well, your variance is your sums of squares divided by n minus 1. Okay, well, how do I get my sums of squares? Oh, yes. So remember those x squared minus quantity x squared over n? Well, the x's become d in this case. So sum of d squared, all right, well, we already summed d, right? But no, that sum of d does not go here. That sum of d goes here. So we need to get a d squared column that we can sum. Remember, this goes all back to those algebra problems and that in those first 3 chapters. Do you remember algebra? PEMDAS, right? Parentheses, exponents, multiplication, division, addition, subtraction. So parentheses first, the e, d squared. So summing d is 64. So in this space, you get 64 squared. Well, now I don't have parentheses. So I need to do, no parentheses is exponents. So I need to square each d and then sum them because addition comes after multiplication, division, addition, subtraction in PEMDAS, your order of operations. So that means I need to go up here and I need a d squared column. So each different score gets squared. So 25, 441, 529, 625. And that sum of those differences squared is equal to 1,620. So now I can plug all of my numbers in. I've got my 1620 over my quantity sum of the different squares, 64 squared over 4. That gives me a sum of squares of 596. I can plug that 596 in. I divide it by my degrees of freedom. I get 198.67 as my variance. Plug that in, divide that by the sample size, and I can get my standard error of the mean differences. So I know that my mean difference was 16. I divide that by the standard error of mean differences. I get my t calculated of a 2.27. So I have, remember, 2 ways to check this. I can check under the p-value, the calculator, by entering the means and alpha and the information that calculator requires. Or I can go to the table and I can look at my alpha and my degrees of freedom, And I found that my T critical, because it was non-directional, right, it needed to be a plus or minus 3,182. But my T calculated was only a 2.27. So that 2.27 falls here. And we say, not significant. We fail to reject the null. We retain the null. It's not significant for this part. But what we do find, the question is, let's just check. We only had 4 kids. Let's see what the effect size is. So it wasn't significant. What if there is something here, even because I only had 4 students? So when I plug in, I get an R square of 0.4, which is a large effect size. How can I have a non-significant score with a large effect size? Sample, right? And so with this sample, you have in these drugs, it's not significantly showing. But what it is saying is that if we had more, this was a wrong example that was supposed to go up. If we increase our sample, this drug probably does show that it significantly decreases drowsiness. And so because also we had one score in our sample that went a different way, this actually improved their reaction time, right? So that could be an outlier, that could be a mistake, but essentially a quarter of our sample pulled it the other way. And so that can be why we're finding a not significant result with a large effect size. So these are your examples to get you through chapter 10. You have a couple problems to solve. And what we're going to do is next week, we'll review all of these questions, every question you have for your SPSS. Those tutorials are also posted within your SPSS directions. And you know where to find me with any other questions. I hope this was helpful, and we'll talk to you soon.